I'm also very grateful to be here and I think honored and humbled, particularly hearing the presentations from yesterday. I think a fantastic quality of work that's been done here. Very inspiring. In fact, I went home yesterday and reflected on what I was doing 30 years ago. I was working at Environment Canada as a student co-op placement that I had there. I was loading and unloading air samplers for largely persistent organic pollutants, PCBs, and organochlorinated pesticides. But I dig up a report that I submitted May 7th, 1993, on where I did a little side project. I pulled out an Anderson air sampler and used it to measure sulfates and nitrates and different particle size fractions and wrote up this report. I've got my acetate overheads, but there's no overhead here for me to give that presentation, so I'll leave that go here. It's an unpublished report. If anybody's interested in that data, it exists. But it sort of gave me the motivation to sort of pursue, I guess, education in the area of environmental chemistry, and ended up doing work on environmental contaminants, PCBs and other POPs, and was interested in their long-range atmospheric transport, and did a lot of work on fate and exposure modeling. And I think to some extent I find myself, this guy over here, doing other contaminants. And I've been doing that for about 25 years, but then 15 years ago, I sort of got introduced to this guy here, microplastic folks, and found myself, I guess, brought into that space of microplastic research. And I think noting that the title within this presentation was meant to reflect on dietary exposure, Steph being the microplastic research, sort of strong-armed me to have a slight change as a follow-up to her presentation, because she reflected on inhalation exposure and concentrations in the air, but it seemed appropriate to perhaps talk a little bit more around the adverse effects side of things. So hopefully that doesn't disrupt too much. But as you can see, microplastic researchers can be disruptive a little bit. And listening to the talks yesterday, I was also sort of thinking about particles, and of course Steph's presentation in relation to the fact that microplastic are in the air and they're sort of all around us. Also sort of springs to mind this guy. Hopefully a lot of you will recognize his character. This is known as Pigpen. He's a character in the animation skit Peanuts, popular for Charlie Brown and Snoopy. One of the characters, of course, is Pigpen. He's always depicted as having this cloud of dust around him. I think the idea is that he never washes, and so he's just always dirty and has this dust around him. And it seems reasonable if you're young and you look at Pigpen, if he would just wash, those cloud of particles would disappear from him. But thinking about the presentations we heard yesterday and the models where we see in London, high population density, big clouds of particles that are sort of being generated. And it seems to me we're all Pigpen because we're all generating particles wherever we go. And I guess the science that we're trying to do is try to identify mechanisms by which we could reduce that cloud of particles that we're trying to reduce. Nevertheless, we will still always have a cloud of particles around us. We just want to limit that footprint that we're sort of creating so that it's not quite so big. Now, on the microplastic story, I think Steph did a great job sort of giving some of that background in terms of the history of where it came from and understanding some of the concerns associated with its use. I think many of you will have seen the headlines, the media headlines around microplastic. The fact that we potentially could be ingesting a credit card's worth of plastic every week, that these particles are entering into our bloodstream, they're accumulating in placental tissues with potential impacts in terms of the fetal development. We have information that because these particles get in the atmosphere, they may potentially be subject to long-range transport in the atmosphere and are contaminating remote locations such as in the Arctic. All of this, of course, is raising a lot of concerns within the general public who are requiring or demanding that some action be taken in terms of perhaps plastic use and try to reduce our exposure associated with microplastic. So there's a sort of an emotive response that I think that comes from the communication around the microplastic research that gets out into the general public, which is something to sort of be aware of. Now, one of the challenges I guess I have when I see these stories is trying to reflect on what it is we're really most concerned about. And here I want to introduce another pop cultural reference to Monty Python and the Holy Grail. Hopefully I don't have to explain too much about who these folks are, but maybe for the younger folks in the audience. This was a very popular British comedy troupe from the 1970s, and they did have a couple of movies, 2-3 movies, and also had a series on television. Some folks really are big fans of Monty Python, some are not. I happen to be one of the folks who are fans of Monty Python. And this particular skit comes from the movie Holy Grail, and for those who are familiar, it's a witch-burning skit where the villagers have sort of identified we'll say, a contaminant of emerging concern. They've identified a witch in the community, and the question is whether or not this individual has intrinsic properties that make them a witch. And from a scientific perspective, there should be ways of telling whether or not the person is a witch. And that's effectively how the skit sort of plays out, trying to identify what is the mechanistic basis to understand whether or not this person is a witch. For me, there's sort of this problem formulation that has to come into play, because if there is an intrinsic property related to a concern that we have, we should be able to use that to identify whether or not there's a risk. Or are we just concerned about a potential harm? And I sort of differentiate between risk and harm in this case because I think they are different things that we're talking about. Harm could be emotional harm. We could be outside and we find litter on the ground. This creates a sort of a negative feeling within us, which is a harm that we're sort of experiencing. And we just don't like the idea that we are littering the environment with plastic. And so if that's the concern, then we should just be trying to implement mechanisms by which we could reduce the release of plastic into the environment. Risk is something very specific. We want to have some sort of dose-response relationship in terms of a contaminant that we're worried about to understand what the potential risk is. We heard earlier today about a number of hazards that we could identify, and Paracelsus in the 15th century identified that everything is a hazard. It's the dose that makes the poison. And I think that's what we are trying to do when we evaluate risk. What is the actual exposure concentration that we have? So problem formulation, I think, is really key. As research scientists, of course, we do want to understand whether or not there's a risk, and is there a relationship between the intrinsic properties of the contaminant and the cause for concern that we might have in terms of a hazard. Now, ideally, I guess in my mind, I sort of think that there's this well-oiled machine that exists in this policy space that brings together all the different stakeholders to identify the scientific challenges and the state of the science that might exist, particular concern, a contaminant that we might be interested in. And that information is very useful for helping to inform what the human and environmental risk might be associated with exposure to that contaminant. Ideally, I would think that this machine should enable a nurture constructive dialogue between the different stakeholders aimed at trying to characterize what are the real hazards, the exposure associated with those hazards, and enable characterization of risk, which can be useful for helping to identify and optimize the most effective strategy to mitigate the exposure we might have to a particular contaminant of concern, such as microplastic. But does this, oh, there we go. And this has happened to some extent, excuse me, where a number of regulatory authorities have sort of evaluated the state of the science with respect to microplastic, for instance. So in 2016, as Steph pointed out, at that time we were mostly concerned about microplastic exposure coming from seafood, as the marine environment was believed to be the source of contamination. EFSA went out and evaluated the state of the science associated with this information and came up with a report, which was also followed then by the environmental risk, the risk assessment group in Germany, BFR, and the World Health Organization, who also submitted or published a report in 2019 related to microplastic in drinking water. Environment and Climate Change Canada, Health Canada, also produced a report summarizing the state of the science, and both Steph and I were also involved not only in the World Health Organization activity, but also in some discussions that were happening in the state of California related to trying to identify a threshold concentration for microplastic that might be present in drinking water in California. I think it's fair to say that a sort of a consensus across all of these different authority assessment reports is that risk evaluation is currently not possible given the state of the science in terms of the concerns that are raised around microplastic. There may be a temptation from these reports, therefore, to conclude that what we need are more data. We simply don't have enough information to sort of enable us to make an assessment of whether or not there is a concern moving forward. But on this point, I want to be a little bit controversial and sort of question whether or not it's more data we need, or is this a question about the quality of the data that are being generated. So since 2004, when the term microplastic was first coined by Richard Thompson here in the UK, we do see this exponential increase in the number of publications that have occurred in the area of microplastics. So last year, for instance, there were more than 3,500 papers that were published on the topic of microplastic, and this year alone, we're well over 1,000 papers that have been published, and we will exceed the 3,500 from last year. There are a lot of papers that are being published on the topic of microplastic. There's a lot of resource being spent on this issue, but there's still sort of questions around whether or not the data that are being generated are of sufficient quality and reliability to enable us to inform our understanding of risk. And I think what is clear in a number of publications that come forward and continue to be published in this space is the need for well-designed, quality-controlled, standardized methods that enable us to characterize what the hazard is, as well as help to inform our ability to understand what our actual exposure to these materials are. So there's a bit of a disconnect in terms of, as Steph sort of alluded to, between what is being tested in the lab and what we are potentially exposed to in the real world. We need this information in order to better understand what are the target tissues that might impact us as humans from a human health perspective, or in terms of identifying which species in the environment might be most at risk of exposure. This information, of course, is really key for helping to inform decision makers in the regulatory community, but also different stakeholders as to what is the most effective strategy moving forward. So you really want to have that scientific information to inform, is this or is this not a risk? Well, as Steph sort of also alluded to, microplastic, what are they? They are a very complex mixture of materials. So we have plastic particles of varying size, shape, depending on, they have different surface chemistries, as Steph pointed out, and we have different polymeric materials that are used in commerce. Depending on how a plastic is used in commerce, it may have different types of chemicals associated with it, and at different levels. So not all plastic necessarily contains chemical additives, and so when you have this big mixture, it's hard to say which ones actually have a chemical associated with it, or is it the particle that's driving the toxicity. Of course, when these particles get in the environment, also we are aware that weathering and aging results in changes to the particles themselves. They may lose the chemicals that were associated with them initially, but as a result of their weathering and aging, may become have a higher oxidation potential associated with them. So there are a lot of factors that are occurring. They also have a biofilm which can form on them, which might influence the formation of an ecocorona, which can influence potential uptake from a physiological perspective. So there's quite a lot going on here. Steph put tire and road wear particles as part of her definition of microplastic. This is actually a bit of a sore point for me because I'm not convinced that we get benefit from including tire and road wear particles as part of this definition. I almost think it would be more beneficial to keep them separate from the microplastic topic. But that gives you a sense of sort of the debate that goes on in this community. Rayon, for instance, is not considered by some groups a plastic material because it's semi-synthetic. It's a cellulosic material. So is it actually a plastic or not? And this also has me step back and sort of question, what is it we're really worried about here? I think we're just generating particles. It could be cotton and wool fibers that we're also generating and putting out in the environment, which could have similar adverse effects to these plastic particles. So I think trying to give context, again, going back to that problem formulation, what is it that we're really worried about is really important to understand. And I think the science that we generate should hopefully help to better understand these various processes that are at play. So this goes back to this idea, is there an intrinsic relationship between the properties of the stressor that you're working with, a microplastic particle, for instance, or any type of particle, and an adverse effect that you see in a particular test system? And when we run these test systems, we want to try to avoid what we might reference as a biophysical interaction versus what is actually an intrinsic adverse effect that might be occurring at a cellular level. If I go back to the image of the witch in the village in Monty Python, they have dressed the person up as a witch, which is sort of a biophysical idea component. The person has an extrinsic or a system-dependent property which implies that they are a witch and may have a hazard of a witch, but they may not necessarily have the magic to change somebody into a newt, for instance. And so it's sort of this need to sort of differentiate what is actually an intrinsic property versus a system-dependent property is really important. On the flip of that, of course, you want to be aware of wolf wearing sheep clothing. So there's sort of these ideas that I think that are really important to reflect upon from a toxicological perspective and relate then the properties to the adverse effect that you're seeing and have a mechanistic basis for understanding those relationships. I think the work that Steph has presented and she just presented is really helpful for demonstrating what is needed to, I think, help improve our understanding mechanistically of what those relationships could possibly be. Now, in looking at the state of the science that occurs within the World Health Organization activity, for instance, that both Steph and I were involved with, it seemed useful to try to consider how we could develop and apply an assessment tool, particularly directed at publications related to reporting adverse effects in both in vivo mammalian systems as well as in vitro toxicity assays. This information that we obtained from this tool was very useful for helping to frame some of the discussion we have in the World Health Organization report, but it was also useful in helping to inform the discussions that were had in the state of California. And we went through this exercise then to try to identify a number of criteria that would be sort of associated with good laboratory practice and when running a toxicological study. So these are just criteria reflective of good QA/QC or quality assurance and quality control guidelines that any group should be following. These are just fundamental things that are important. And I'm not going to go into detail about each of these criteria, but I do want to flag that there are sort of three main areas that we want to reflect upon. Those related to how well a study summarizes data related to the characterization of the particles that they're testing, how well they report on the design of the study, and I think importantly for risk assessment, what is the applicability of the study for helping to inform the decision-making process? Is the information actually applicable in that risk assessment space? And so we would go through each of these criteria in a particular study and score them on a basis of 0, 1, and 2. A 0 reflecting that the group did not report particular criteria, a 1 reflecting that they met a minimal level of requirements that we deemed necessary, and a 2 going above and beyond what we were looking for, which could be particularly useful for working towards mechanistic understanding. Now, ideally, for a study to be reliable, each of these criteria have equal weighting, and we would want to see a study score at least a 1 against all criteria. So this is just to give you a summary of the total scores that were assigned to the 76 studies that we looked at, which in this case were in vivo studies that included both oral ingestion and inhalation components. Exposure pathways, and what you'll see, of course, is there are perhaps a handful of studies which have a good overall total score, but the majority of studies are sort of in the middle or poor in terms of the overall quality scoring that we have. Not one study actually scored a 1 against each criteria that we assigned, and so we would, from this result, sort of conclude that none of the studies based on this evaluation would be reliable in terms of helping to inform our understanding of an adverse effect. Now, to give you sort of a sense of some of the trends that we see in the data, I produced this heat map, and you can see a lot of red, for instance, around some of the criteria around particle characterization. And I think this is really important to reflect upon, because when you're testing these particles, we want to know, is there an intrinsic property associated with the particles that is causing an adverse effect? What most groups are typically not reporting is whether or not there are chemical contaminants associated with the particles that they're working with. And so we don't know if the adverse effect that is reported in a study is due to the particle itself, or is it due to a chemical contaminant. Included in this, in terms of particle toxicology, is also important to reflect on whether or not there's an endotoxin associated with the particles, because not only a chemical but a biological response could also drive an adverse effect. So those were two categories that the majority of studies are just not addressing in terms of their study design. In terms of risk assessment, we also see some challenges moving forward. Those challenges typically relate to the fact that few studies include a dose-response relationship. What we typically see are studies using very high concentrations and getting an adverse effect, and so reporting results that are only associated with one high concentration. As a result of that, it's unclear whether or not there is, again, an intrinsic relationship between the properties of the particle and an adverse effect, or as the group just sort of overwhelmed the organism that they're working with, just put so much sort of a foie gras approach in terms of exposing the animals that they had and just getting an adverse effect that had nothing to do with, that was unique to the particles they were testing. So we didn't have anything that was relevant, or a few studies dosing their animals at environmentally relevant concentrations, or using particles that would be relevant to this mixture of particles that we're typically exposed to. As Steph pointed out, most studies are reporting results related to polystyrene spheres of a particular size, typically less than 10 microns. And so we have this disconnect, an apples and oranges thing going on when we're trying to take the effect data that's being reported in the literature to what we know is in terms of the exposure and put those two together. We just can't do that because we don't have a read-across approach that makes that possible, which is why we can't say anything about the risk associated with these materials moving forward. Nevertheless, as again Steph pointed out, there are some sort of consistencies across studies in terms of different adverse effect endpoints that people are reporting. It seems clear that oxidative stress formation is a key pathway that results in inflammation, and we note this as a result of a number of different cytokine biomarkers that have been reported in various studies, which may or may not result in cellular death. There are these other effects related to lipid and energy metabolism that have also been reported, but it may not necessarily be clear what the direct relationship is between these different components in these studies. So as a concluding component within the WHO report, we sort of reflected then on the fact that the adverse effects that are being reported for microplastic are consistent with other well-studied solid insoluble particles, because these modes of action in terms of inflammation, oxidative stress are not necessarily unique to microplastic. This occurs for a number of different contaminants. What we do need, though, is then studies that actually characterize the hazard of materials that are more consistent with what we are exposed to in the environment at environmentally relevant concentrations. And so that would be very helpful in terms of moving forward. And also, it would be very helpful if studies would focus on, I guess, adhering to good quality assurance, quality control practices in order to obtain reliable and relevant data that could be used in that risk assessment space. So how do we prioritize research moving forward, I think is really an important question. Clearly, there are negative effects that are occurring. We know that we have an exposure. We're all sort of pigpen, and we're generating these particles wherever we go because plastic is also with us wherever we go. And so trying to clarify what the risks are and which properties are influencing those adverse effects is really important to help, again, direct decision makers in terms of identifying actions that's most important. This brings me back to this stakeholder component in terms of problem formulation. And I think what would be helpful to get these stakeholders together to sort of reflect upon how do we generate reliable and relevant data. Now, what I would say is that the ability to develop standard methods is not the most sexy thing. It's not going to get headlines in the BBC, for instance. And generating environmentally relevant reference materials is also not very sexy topic. But it is really important to have this type of research that's being done to sort of move things forward. And it would be beneficial to try to get these groups together to work in an effective way. Now, for the more astute of you, you will notice that this machine that I put together actually won't work. And I think this just is reflective of the political space in which we all operate. I think I was hearing a lot of that in the discussions earlier today in terms of the policy-science interface. There is a lot of frustrations because stakeholders have different biases, different political agendas that they're trying to work towards. And I think that complicates things a little bit in terms of trying to make progress on some issues. Now, I do want to end a little bit more optimistically, because I think if we could get stakeholders together and get them to work in a way that really focuses on trying to generate good quality science to help inform that decision-making process, we can avoid the idea of a witch hunt moving forward and actually do things in a very effective way. And so I tried to do that, and hopefully this is what we're kind of looking forward in terms of things moving forward. Now, last couple of weeks, there's been Paris discussions in relation to a international plastics treaty. I know there's some frustration in terms of perhaps lack of movement, but again, I'm trying to be optimistic that hopefully that will move forward and we will see some benefits in terms of trying to reduce the release of plastic in the environment, which I think would have a knock-on effect in terms of helping to reduce our overall exposure to microplastic moving forward. So just want to end with acknowledgements to those who provided financial support for me over the number of years, particularly to the World Health Organization and the support they gave me towards helping to develop that report that was published last year that Steph also pointed out to. So thank you very much.
Thank you. Perfectly on time. Okay, we've got time for a few questions or a bit of discussion. So Tim, do you want to start?
Thanks, Todd. I'm just wondering, I saw your kind of mapping or heat map of the particles. In terms of actual particle hazard, which is more important, the chemistry of the particle or the physics of the particle, i.e. the shape and size, surface kind of structure?
I think, well, for me, in terms of the microplastic space, that's where I think there's an opportunity to bring in particle toxicologists, because I have a sense that there's been many decades of research in the area of particle toxicology that have tried to address what is the most important thing. Is it the surface area of the particles, for instance, that results in an adverse effect, inflammation? What is it that's really driving that adverse effect? Is it chemical, or is it some sort of structural component of the particle? And in a way, I often think that in the microplastic space, maybe there's an opportunity to take advantage of the resource, the funding opportunities that are there to not only look at the microplastic issue, but perhaps expand more broadly to all of particle toxicology to try to answer these kinds of questions. But based on the research that's been generated to date, there's not enough information to say, is there something that directly relates those aspects?
Okay. There's a question at the back. Sorry.
Yeah, thank you very much. There's obviously still a lot to learn. I'm just wondering whether whether any of the studies that are available have tried to compare the toxicity of microplastics with the toxicity of other particles, and so whether you can do any kind of comparison that way. Thanks.
Yeah, and so far, a number of the studies are just focusing on the plastic particles themselves. It is a recommendation, I think, that we've also proposed within the WHO and other activities have been involved with, to consider the use of some sort of reference particle, both a positive and negative control, that could be used to try to bring context to the results that are being reported. I think this is sort of a failing that exists, but it might be consistent with any new contaminant emerging concern where people just get carried away and are doing the research, and hopefully what will happen is these kinds of practices will come into play. Because, yeah, I think this is a really important thing, and it reflects also the response from Tim in terms of trying to understand what that potential relationship might be.
Okay, any more questions? I just may ask one quick question, just related to what Tim says. If you have a certain sort of plastic, do they always break down to form the same shapes? Because if you have a shape like hazard, like with asbestos, with a high aspect ratio, do you always get long, thin from some plastics and short, fat from others, or is it just random?
So that I think there's sort of also additional research and sort of trying to take place in that area. I've been interested in the thermodynamic aspects around how particles break down, again, in a more generic way. So there's research that's been done to try to understand that fragmentation of particles, how they kind of break down. It seems as though and it will depend on the structure of the polymer that you have. So a linear polymer, polyethylene, will likely behave differently than something that has a lot of co-branching associated with it, and that will influence the fracturing that occurs. And so you have to start thinking about the physics around how that fragmentation takes place. If I reflect upon that weathering and aging piece, so if you have something out in your back garden and it's been weathering, I think what happens is that, yeah, you just have this shedding that's occurring at the surface of the plastic, and the stuff is flaking off. And so, but again, it might depend on the polymer that as at play. So you might see differences between nylon and polypropylene, for instance. So yeah, I think we need to think very specific about the polymers that are there, which is why I think I'm critical of the definition, because not all microplastic are equal. They don't all behave in the same way, and it might be beneficial to silo the different polymers into ways that might answer some of these questions.
Okay, thank you very much.